Hello and welcome back to my game engine series, where I try to make a game engine in C++ and Vulkan. I've been working on a small-scale space game recently. The whole point of this is that the game design should be driving the technology that needs to be in the game engine, rather than endlessly trying to create technology that I might not even use. And I also want to see if it's even possible to make a game in this game engine. And while making this game, I went through a bit of an odyssey, and that was all to do with performance and the frame rate. The frame rate was originally running at 16 frames per second, and after a lot of work, I got it up to 5,000 frames per second. The frame rate started to get really bad when I started to add physics to the game. To do this, I've been using the Jolt physics engine. Any type of game, but especially 3D games, need some kind of collision detection system in place, so you can interact with the game, rather than just being a floating camera that passes through everything. Right now, I'm only dealing with sphere versus sphere collision detection. When it comes to 3D collision shapes, this is the simplest type of collision detection that you can do when it comes to 3D collision detection. I also added a debug renderer to the game engine. This is going to render things that the player won't see, and is purely designed to help with game development. In this case, I'm just rendering the collision geometry shapes so I can see what's going on. This is just a visual aid so I can exactly see where the collision detection is happening and being resolved. As the models in the game engine won't ever exactly match up with the collision geometry shapes, I am aware that the Jolt physics engine has its own debug renderer, but I decided to go with my own, so I can use this debug renderer for other things other than collision detection. So everything was going well until I increased the number of asteroids to 4,444 for a demo scene. And in debug mode, this is where I got 11 frames per second, which was taking 89 milliseconds to draw the whole frame. And when I turn off the debug geometry, this is where I get 18 frames per second, so that was taking 53 milliseconds to draw the whole scene. This is beyond terrible for a couple of reasons. The scene I'm trying to render is very simple. I've actually turned off all lighting, and there's basically 2 models being rendered, not including the debug renderer. The next thing, I have a pretty decent graphics card, the NVIDIA 4070. And the final thing is, one of the points of making a game engine is that you can cut things out, making things run typically faster in your specific case than a commercial game engine. So in all accounts, 16 frames per second in release mode is absolutely garbage. So obviously something's seriously wrong here. As I have an NVIDIA graphics card, I have access to a tool called Endsight, which is a tool that you can use to profile your GPU to tell you what it's doing. And if you look at this, it's incredibly obvious what's going on. You see that yellow graph? That is telling me the GPU utilization rate. And as you can see, there are massive gaps. We have a utilization rate of 20% here, meaning for 80% of the frame, the GPU is doing nothing. This tells us one thing. The problem is actually on the CPU. Well, the first thing I tried to do was remove this piece of code at the top of the frame called the VKQA idle function. When I profiled this with Endsight, this function by itself takes 0.23 milliseconds just to execute. What this command does is it pauses the main queue. And in our case, the main queue is the presentation and the graphics queue, meaning that the presentation and the graphics commands all have to finish executing before we continue on the GPU. This is effectively a big mutex lock at the beginning of the frame for both the CPU and the GPU. The reason I added this originally at the beginning of the frame was to stabilize the renderer. If I remove it, yes, things get faster, but the renderer gets incredibly unstable, and we get graphics corruption, things slipping around. I needed to solve all of these issues, because the VQA idle command at the beginning of the frame is unacceptable. So that's where I started. Synchronization in Vulkan is one of the hardest parts of Vulkan to get right. For a long time, the Lunar-G validation layers couldn't pick up if you made a mistake in your synchronization code, because it's also really hard to test. Even the Mastering Graphics Programming book with Vulkan and the Vulkan tutorial from 2016 made similar mistakes with their synchronization code. If you do actually want to learn Vulkan, I do highly recommend the How to Vulkan or the Vulkan guide online. They're both up to date and correct, instead of using the Vulkan tutorial from 2016. So on top of getting synchronization wrong in Vulkan, there was also some graphical corruption, which can cause some terrible flickering, and graphics drifting around. So we have all sorts of issues that we need to fix before we can even consider the idea of making a video game. But that's not why everything is so slow. If you remember what I said earlier, the CPU is the issue, not the GPU. Even with the synchronization issues fixed, we're still only using the GPU about 20% of the time per frame. And if you've seen other videos of mine, you've seen that I'm able to render more complex models that use different materials, and here I am choking on a very simple model with no lighting. What is going on here? Well, part of the problem is I decided to move away from render passes and into the future with dynamic rendering. The upside of using render passes is that you get to think about the images and how they're going to be used by the next render pass. This allows you to set up synchronization ahead of time, and when you run all the render passes, the synchronization is basically automatic afterwards. And I set up these dependencies between render passes with something called subpass dependencies. The general downside of using render passes is that it adds a lot of complexity to your renderer without giving you much in return. If you're not targeting mobile devices, the recommended way forward is to use dynamic rendering, which basically removes the need for a frame buffer and subpasses, and you don't have to worry about building image dependencies ahead of time with your render passes. This is another reason why I started again with this game engine, is because I wanted to simplify everything. So moving to dynamic rendering away from render passes was a no-brainer. But what I didn't know at the time is I've lost something along the way. I've lost that synchronization between the render passes, and because I use subpass dependencies, all those synchronization guardrails I had were completely removed. So the first thing I had to fix were the fences, semaphores, and pipeline barriers. The pipeline barriers and the semaphores were completely wrong. It's a very common mistake in your pipeline barriers to use the current frame that you're on instead of the Vulkan image index, which is something you get from the presentation engine when you acquire the image with the function vk_acquire_next_image. After adding the Vulkan image index to the image semaphore and the pipeline barriers and learning how the pipeline stages actually work, I got rid of some of the synchronization issues. I then turned my attention to the dynamic rendering. You use these structs at the beginning of each frame to set up the dynamic rendering. I also had made the same mistake here with using the current frame instead of the next frame index, which is something I corrected with the pipeline stage. So once I worked this out, this was an easy fix. So at this point I had mostly cracked the synchronization issues, but we had barely increased in FPS at this point. At the very least I could get rid of that vkqa idle function. The next issue could be solved by simply opening up RenderDoc and running my engine through it. RenderDoc is a graphics debugging tool that's agnostic to any type of graphics card. It basically intercepts the command that you're going to send to the GPU, allowing you to see what the graphics card is going to display, based on the commands that you're going to run. So if you're a graphics programmer, you can probably immediately see what's wrong. We are doing 31,155 draw calls to render this one scene. This scene is incredibly simple. This shouldn't be an issue. This is extremely inefficient. There are so many ways to reduce the amount of draw calls, and I'm not leveraging any of these techniques. Now if you look at this scene, there's a lot of repeating entities. With that in mind, we can leverage something called instant rendering. It allows the GPU to render things many times, and we just index into a position buffer that tells the GPU where to put it. Effectively a copy and paste job, with the position only being different each time. If we do that, we reduce the amount of draw calls down from 31,155 to 3. And at that point we just sped up the game engine to 750 frames per second. So each frame was taking 1.34 milliseconds to run. The next thing I had to fix for my own sake, and anyone who was watching me live coding this game engine, was the flickering. This was strange because I was getting no results sometimes, everything looked fine, and the next minute the graphics looked like they were strobing. This started to get worse and worse as the renderer speed increased. Fortunately, even though the error didn't turn up all the time, this took a while to find, but it was pretty straightforward once I found it. I was allocating a buffer that was too small. You see, I've been trying to move towards something called bindless rendering, and part of the effort towards bindless is to use buffer device addresses, which are basically just buffers that you index into with a pointer, so effectively it's an array. However, the GPU doesn't know if you've gone out of bounds. It will just keep reading, unlike the CPU. You have to be careful with this particular type of error. It's called an out of bounds read. You can actually crash the graphics driver, or even worse. So if you allocate a buffer too small, and you index past that point, and you don't have synchronization validation layers turned on, which I hadn't at the time, the GPU will just keep reading, and you'll get completely undefined behavior, which includes things working. So once I had found that I was allocating a buffer an order of magnitude too small, the graphics corruption completely disappeared. Even with all those fixes in place, we got to a frame rate of 1600, so the frame was taking 0.51 milliseconds to complete. Now all the stabilization issues were gone. We're still using roughly around 40% of the GPU, which really hasn't solved the problem. We've made the renderer faster for sure, and all the fixes were needed, but if we don't figure out why the CPU is pausing the GPU, this is going to scale terribly once again, as we add more things to the game engine. But there's just going to be more stuff on the screen this time. So this time I investigated the physics engine, and it turns out I was updating every single rigid body in the scene, regardless if it's moving or not. So those 4,444 asteroids that are floating around are non-moving static geometry, which are taking part in the physics simulation, but I don't need to update the position. And if you haven't set up threading in your engine, which this engine doesn't currently have, you're punished immediately if you make a mistake by accessing the physics engine over and over again in this way. So what I did is I put all the static geometry on a non-moving layer in the physics engine and stopped updating anything that wasn't dynamic. I also stopped updating dynamic geometry if it went to sleep. When a dynamic object goes to sleep, it doesn't take part in the physics simulation anymore, which helps with performance. So the position doesn't change, meaning I don't need to update the position of the object either on the GPU. This was the entirety of the CPU overhead, and what was causing the GPU to be completely underutilized. Because the physics engine is designed to be threaded, and I'm currently running it in a single-threaded environment, it's running on the rendering thread as well, meaning that everything gets paused so we can update the physics engine and update the positions. So there was a really simple fix here. The static geometry doesn't need to be updated, and therefore I can add a countless amounts of static geometry without any issue at all. The bounding volume hierarchy can be built, and everything's fine. Once I had done that, the frame rate hit 5,000 frames per second when disabling the debug geometry. And if you look at Nsight too, we're basically using the GPU 100% of the time now, which is exactly what we needed. This is fantastic because now we can start adding stuff to the game, make the pixels prettier, and adding some gameplay to this game, without worrying about things falling to 10 frames per second. One thing I've learned from this process is how much more I need to learn and get better as a developer if I want this engine to be actually useful. Like I mentioned earlier, I really need to add threading back into the engine. I've recently been working harder than I've ever been on this particular project, but I've still got a long way to go. I just want to give a quick shout out to all the people who have joined in with my live streams and helped me out with this project. Seriously, thank you all for the help. So that's where I'm up to with my game engine development. I hope you all enjoyed this video and are happy with how much progress I've made. Well, I'll see you in the next one. Bye.